neue Freigabe. My goodness, what is it worked?
Yeah, to the others, just let me mention that last time I did record and Bernardo also reminded me, but the recording didn't go through this time because uh, this is done first via cloud computing, and the company which organizes this cloud computing is just the one who had worldwide problems exactly last Monday and Tuesday. So it was not our fault that it didn't work. It was a worldwide failure, and so we don't have a recording of the last time. But this time everything should work, and the recording is running. And Gerhard, please start.
If I now push Bildschirm freigeben, it's all right.
Yeah.
Okay. No, it isn't.
Yeah, looks good.
We can see in your desktop, so it work.
You can see my yeah, well, but I want you to see the charts I prepared.
Yeah, you have to open it, this file. No. You have to on your desktop. You have to find the file where the Omdruck for today is.
Okay, yes, I have to, I need the file, but then this should be fine.
Yeah, looks good.
Yeah. Okay, we have
Very
it.
good.
We have it. Let me, no. These pictures.
Yeah. So you're all set.
Okay. I think we could start. Yes. The last session. First of all, very welcome. The last session ended with a result that a near-ring is semi-simple in the sense of black hat if the J2 radical of this near-ring is 0. And yeah, this should be on page 92, but page 92 had no space. Semi-simple in this context is meant to be semi-simple in the sense of black hat. Now this theorem with which I ended the last session, this follows easily from the following proposition. Let K be an N plus subgroup of N plus. We call K nil if all elements of K are nilpotent. In other words, if for all K in K there exists an R such that K to the R is 0. If this is the case, then K is contained in J2N. First, the proof of the theorem with which I ended the last session. If N is not semi-simple in the sense of black hat, then there exists an N subgroup K of N plus, which is nilpotent even. And this means that we have an R such that K to the R is 0. And by our proposition, this K must be contained in J2N. Conversely, if J to n is 0, then n contains no non-zero n subgroup K, which is nilpotent, and this means n is semi-simple in the sense of bracket. That's very, very easy. The proof of the proposition goes as follows. Assume K is not contained in J2 K as mentioned in the formulation of the proposition. K is not contained in J2 of n, then there exists an n module gamma of type 2 such that gamma K is not equal to 0. Hence, there exists a gamma non-zero in gamma such that gamma K is non-zero. That's a consequence of this is non-zero, and gamma K is an n subgroup of gamma, and since gamma is of type 2, we have gamma K is capital gamma. So there exists an element K in capital K such that gamma K is gamma. And you may repeat this process, multiply with gamma, then you get gamma K squared as gamma K is equal to gamma, and so on. So for all integers, for all s, gamma K to the s is equal to gamma. But for a suitable r, K to the r is 0. This would mean that gamma is 0 in contrast to what we have chosen. So this cannot be the case. We have the situation that K is contained in J to n. Definition and remark, let K be an n subgroup of n plus nilpotent. We have the concept of nilpotent. As mentioned, there exists an integer s such that K to the s is 0. This means that any product of s elements of K vanish, no matter how we choose these elements. K nilpotent implies K nil. It implies that every element of K must be nilpotent. The converse is not true in general, but that's a different matter. Let me formulate the following theorem. N is a Near-ring with left identity E. Then Dn, or in the notation of Wilder-Pilz, J1/2, Dn contains all nilpotent right ideals. Proof. Let K not equal to 0 be a right ideal, which is nilpotent, which means K to the s is 0. So any product K1 up to Ks is 0 for all possible choices of the Ki from capital K. Now that R be a maximal right ideal of n, since n contains a left identity, R is modular. We have to show K is contained in R, and hence in the intersection of all those R, and that's then Dn. Assume K is not contained in R, that's always the trick. Then K plus R must be n, K is maximal. So the left identity E is equal to K plus R, K in K, R in R. And if we multiply from the left, with k plus r, k1, k2, up to ks minus 1. This must be, since k is a right ideal, this must be congruent to k1, ks minus 1. And this is a product of s factors, and this is 0 modulo r, since r is a right ideal. Similarly, we have k1 up to ks minus 2 is equal to k plus r, k1 up to ks minus 2. This is congruent modulo r, k1 up to s minus 2. And this is, as we have seen, congruent 0 modulo r. And repeating this argument leads to k1 in r for an arbitrary k1 in k. Hence, k is in r. And the corollary in a Near-ring with left identity, if J1n is nilpotent, then J1n must be contained in D of n, but D of n is contained in J1n. Hence, J1n is equal to Dn. Similarly, if E in n and J2n is nilpotent, we conclude J2n is equal to Dn or J1/2 n. Remark, Lexton, in his paper in Journal London Mathematical Society 38 in 1933, this is possibly part of Lexton's thesis. He was able to prove if n is distributively generated with an identity, and with the minimal condition for n subgroups of n plus, then Dn itself is nilpotent. I remind you, n distributively generated means the semigroup of distributive elements, two-sided distributive elements, generates the additive group n plus. Well, for lack of a proper heading, I call this continuation. The following theorem is due to Fine. He wrote a thesis on Near-rings in 1968. Let R be a right ideal with a property that R to the k is contained in J nu. Nu may be 1 or 2, not 0, 1 or 2, and some k. Then that's not very good. I should have called this R to the s. K was an element in the Near-ring. Here it is, of course, an integer. If this is the case, then R is contained in J nu n. Again, that's always the machinery. We assume that R is not contained in J nu n. Then there exists an n module gamma of type nu such that gamma R is not equal to 0. Hence, we have a non-zero gamma such that gamma R is non-zero. And this must be, since R is a right ideal, this must be an n submodule of gamma. But gamma is of type nu, hence gamma R is gamma, and also gamma, capital gamma R is gamma. So we have the machine, or well-known machinery, gamma is gamma R, it's gamma R square, and so on, equals gamma R K. For the K we identified before, but R to the K is 0, so gamma R K is 0. And this must be, this R to the K must be in J nu n. So we have a contradiction to our assumption. R is not in J nu. Remark: if nu is 2, the result remains valid if R is an n subgroup of n plus. Corollary: Jn contains all nilpotent right ideals of n. J2 contains all nilpotent n subgroups of n, or n plus. There is a lot more to be said about these Jacobson type radicals, but I want to make a kind of interruption. Well, oh, no, that is not good. I would like to talk on distributive sums. That's the generalization of direct sums, but with special with a speciality which is due to the Near-ring case. The goal is, if we have the situation that these J nu are 0, and if we have suitable minimal conditions, chain conditions, then normally we are able to decompose our Near-ring into smaller parts, and this the proper concept for these direct sums is distributive sum. We'll be clear in a moment. And yeah, that I should say that we shall look at a back of examples, and these examples are quite frequently distributive sums, so I have to explain what a distributive sum is. Assume we are given gamma 1 up to gamma s n modules. Now, it's clear what we mean by the direct sum of the additive groups gamma I. We could define, so far these are, we could define this as in this way: gamma 1 up to gamma 0 times n is gamma 1n up to gamma sn. This turns gamma into an n module, and was a suggestion by Wieland. It's a bit more than a direct sum. It's properly called distributive sum of gamma I up to gamma s. Conversely, if we are given an n module gamma with submodules gamma 1 up to gamma s, then gamma plus direct sum of the normal subgroups. Yeah, these yeah, these gamma 1 to up to gamma S should be normal subgroups. We start with the situation that gamma is in the normal group theory sense the direct sum of these gamma 1 additive group, gamma S additive group. Then the n module gamma is isomorphic to the distributive sum of the n submodules gamma 1 up to gamma S. It's tedious always to consider these isomorphisms. We simply say gamma is the distributive sum of gamma 1 up to this should be gamma S. The notation is gamma as usual, and we are in this context only interested in distributive sums, not so in direct sums. Now, to justify this, I have to prove that gamma 1 up to gamma S, these are submodules, times n is gamma 1 n up to gamma S n. And remember, our assumption is that if we look at the additive group alone, then we already have a direct sum. So I have to prove this assertion star. Well, gamma 1 up to gamma S minus 1 plus gamma S times n is it's gamma a certain gamma prime plus gamma Sn, and we could this also put on the other side, because we are dealing with normal subgroups here. The gamma prime is in the sum of gamma 1 up to gamma S minus 1, and gamma S is in gamma S. Furthermore, minus gamma 1 up to gamma S minus 1 times n plus gamma prime is gamma, a certain gamma, and this is gamma S prime minus gamma Sn. This is, well, that's easily derived from the definition of submodules. Now, this is in gamma S, and on the other hand, it must be in the sum of all gamma index j not equal to S. And this is 0, because we started with a direct sum of normal subgroups of the additive group of gamma. Hence, we have gamma S prime is gamma Sn, and gamma prime is this bracket times n. So we have gamma 1 plus gamma Sn is gamma 1 plus gamma S minus 1 times n, and gamma plus gamma Sn. The repetition of this argument completes the proof of star. In a similar way, we define a nearing n to be the distributive sum of its right ideals. That's, we consider simply the n module n plus as distributive sum of certain right ideals. And moreover, in a similar way, we define the distributive sum of near rings n1 up to ns. We form the product set n1 up to ns, these vectors, n component n vectors, ni in capital Ni. We define addition and multiplication component-wise. Then addition and multiplication component-wise, and then we obtain a near-ring n named the distributive sum of near-rings n1 up to ns. The sets of this form, the component number I is Ni, and the others are 0. Ni and capital Ni form ideals in I. This is an easy computation, which are isomorphic in a very obvious trivial way to Ni, and we may be identified with Ni. Conversely, if the nearing n with ideals n1 up to ns is the distributive sum of the right ideals n1 up to ns, the right ideals up n1 up to ns, then the nearing is isomorphic to the distributive sum of the ideals n1 up to ns. For the multiplicative law, must be this one, called mult abbreviation. This is true, and this is very, that's more to that in a moment. We say n is distributive sum of its ideals n1 up to ns. To prove this relation mult, we proceed as follows. N plus is the distributive sum of right ideals n1 up to ns. Hence, if we have such a product n1 plus and so on plus ns times n1 prime up on and so on ns prime, then we since the n's are right ideals, we can we have this n1 up to this bracket n2 and so on ns up to this bracket, and then we have the distributive law, so we can remove the brackets, but then we would have a bunch of wild products which we do not want. Now Ni times Nj prime is contained in Ni and J, and that's contained in the intersection, and then we started with direct sum. This is 0, so the rule mult follows. These decompositions were developed, I think, in the context of representation theory of groups. One wanted maybe group with complicated defining relations represented by a sum of invertible matrices hopefully over a commutative field, and that was much easier to work with. And then here we of course have no matrices, but possibly simple near-rings. Theorem: let gamma be an n module and we have a finite family. Yeah, now how can we recognize? How can we determine is a certain structure a direct sum or a distributive sum in our case? And that's yeah, well-known formulation certainly. Let gamma be an n module and delta 1 up to delta s, a finite family of maximal proper n submodules of gamma with the property that the intersection of all these submodules is 0. But if we omit one of these maximal n submodules, we get n module gamma I, which is not equal to 0. Then we can show n is the distributive sum of the n submodules gamma 1 up to gamma s, and the gamma 1 up to gamma s are irreducible. That's because, well, they are isomorphic to a certain irreducible structure. Well, long hyphen, I have to add a few more theorems and results on distributive sums and how they are applied. These results normally follow from the vanishing of the Ju or J1/2. But I decided that it might be reasonable to interrupt the main course and start a series of examples, so you can see that all these concepts which we derive have a reasonable meaning. Definition and notation. I start with an additive group, and I take the smallest non-negative residues modulo 4. It's almost ridiculous how small these examples are, and still you can see quite a few of our results in action. This cyclic or monogenic additive group has exactly one subgroup. This is 0, 2. M, let be M0 gamma, the nearing of all mappings of gamma into itself, leaving 0 fixed. An element of M is written in this form 1, 2, 3. This is the element which leaves, of course, by definition, the 0 fixed. 1 to 2, 2 to 0, 3 to 1. That's just one example. And now we use this very simple structure to form four examples, which I think are quite informative. The first example is n plus. That is am of delta. All those mappings which map 2 to 0 and of course 0 to 0. Now, gamma is a strongly monogenic N1 module. Any element of N1 maybe act as a generator, unless it's an element which annihilates everything, including 2. Gamma is a strongly monogenic N1 module. Delta is an N1 subgroup of gamma, of course, but not an N1 submodule, because if you take N from N1 to be the element which annihilates 1 and 2, and leaves, for instance, leaves 3 fixed, then we have 1 is congruent modulo delta. The odd numbers in this group are congruent, as well as the even numbers. But if I map 1 by n and 3 by n, 3 n is 3 and 1 n is 0, and this is not congruent, hence delta is not an n submodule. This means that the N1 module is gamma is an N1 module of type 1, not of type 2. Because it has a non-zero N1 subgroup. Furthermore, A N1 gamma is faithful. Hence, N1 is 1 primitive on gamma. And that means, since J1 N1 is the intersection of the primitive ideals, that J1 N1 is 0. So if we may say it's J1 semi-simple. This N should be cancelled. That's nonsense. N1 plus is the distributive sum of finitely many, in fact, 2 right ideals, which are n isomorphic to gamma. And since gamma is not of type 2, there is no N1 module, because if there would be a module of type 2, it should be N1 isomorphic to a minimal right ideal here, and there is no right ideal which is of type 2. Since gamma is not of type 2, there is no N1 module of type 2. Hence, J1, a J2 of N1 is N1. The intersection is empty. But J1 N1 is 0, and that's not equal. So we have an example where the 2 Jacobson radical are often of a very, very small, handy nearing, in which the J1 and the J2 radical are different. N1 equals J2 N1 contains a left identity. When I first talked about near-rings in ring theory meetings in Wolfach or so, people were shocked by dealing with radicals which contain an idempotent. Decent radical has to be nilpotent, but it isn't. N1 contains a left identity, which is of course an idempotent. And according to previous results, which I offer in a week, N1 has only trivial ideals, and it is easy to show that A and 1 of 1 and A and 1 of 3 are the only non-trivial right ideals of N1. N1 contains nilpotent N1 subgroups, which do not consist of 0 alone, except, for instance, all the N from N1, which map gamma into delta. If you square such an element, it must be 0. Okay, let our second example, let N2 be AM of 3, annihilator of 3. Again, gamma is strongly monogenic as an N2 module. Delta is not an N2 subgroup because we have elements which move 2 to a different element, not to 0. Hence, gamma is of type 2. Gamma is of type 2. The annihilator of N2 in gamma is 0. Hence, gamma is a faithful N2 group. Hence, gamma is faithful N2 group, and N2 is too primitive on gamma. That means J2 is N2 equals 0. And the additive group of N2 is a distributive sum of finitely many right ideals, which are N2 modules of type 2. And they are all N-isomorphic to gamma. We also remember N2 is the annihilator of 3, so this is a left identity of N2. Again, we have a left identity, so all right ideals are modular. It's very easy to see that the additive groups of N1 and N2 are isomorphic, and the isomorphism is given by the following. In the first case, we have, let me remind you, that's A of delta, and the second is A of the element 3. We have in N1, 1 is mapped to some element 1 in 1, and 1 times N2 are equal. So on 1, the two near-rings act in the same way. 3 times N1 is the same as 2 times N1, because N2 is the annihilator of 3, so we have to rearrange things. One can show, if one has not a better idea, just make a full list of all the elements, but that's tedious. I do not recommend that. One can show that AN21 and AN22 are the only non-trivial right ideals of N2. And now look at the lattices of right ideals, N1 and N2. They both have this simple square lattice. They are isomorphic, that's obvious. These are isomorphic lattices of right ideals. Nevertheless, N1 has J2 equals N1. That's in the terminology, that's a radical near-ring. And this is a semi-simple near-ring because J2 N2 is 0. The consequence is that the lattice of right ideals seems to be relatively irrelevant for radical theory. That's quite important for me personally, because when I started my thesis, my supervisor had the idea I could study those near-rings with a distributive lattice of right ideals. And I convinced him with such simple examples that this is not a good question. It doesn't lead to much. All right. N3, this is the nearing of those n which map delta into itself. N1 is a subnearing of N3. Cool. Sorry, of N1. It's yeah, mistake. Gamma as an N3 module is irreducible, and an N3 module is monogenic, but not strongly monogenic. Hence, N3 is hence gamma as an N3 module is of type 0, not of type 1. And delta is an N3 subgroup of gamma of type 2. If we look at these intersections of annihilator right ideals, we see the intersection of one of these right ideals with the sum of the remaining ones is the intersection of all annihilators, and that's 0. Hence, N3 is the distributive sum of right ideals mentioned above, and the summands are just these intersections of two annihilators. If we consider gamma, the mapping of gamma onto A1 onto A2, intersection. We consider the mapping of gamma onto the intersection of A1 with A2, such that gamma is mapped to this particular mapping. Then this is an N3 isomorphism. Hence, A1 intersection A2 is an N3 module of type 0, but not of type 1. And in a similar manner, we obtain an N3 isomorphism from gamma to A2 intersection with A3. This mapping, which leaves everything fixed, is an identity in N3. Hence, J1 and J2 must be equal. A1 intersection A2 consists only of 2 elements. This must be a right ideal, hence a right a module, N3 module, but it contains only 2 elements and must be of type 2. So yeah, the intersection of all Dn3 is 0, and in every n module of type 2 is N3 isomorphic to A1 to intersection A3, hence N3 isomorphic to delta. And therefore we have J2, N3 is a delta, that's N1. And since we have an identity, as I already mentioned, we have J2 of N3 equals J1 of N3. This is not equal to D N3 or J1/2 N3. The left identity of N is again an idempotent element not unequal to 0 in J1. Hence J1 is not nilpotent in general. Lexton, in the paper already mentioned, yeah, I had to correct something, and there should be a 9. It's 1963, not in 1863 or 1563. Lexton was a contemporary of us. Bob Lexton, in his paper, Journal London Math Society 38, could prove there exist finite distributively generated near-rings with identity in which J2 equals J1 is not nilpotent, even in the distributively generated case. And in the same paper, Lexton did prove if N is a distributively generated near-ring with identity satisfying the descending chain condition on N subgroups, then the N is nilpotent. Well, number 4, we form the direct sum of gamma and delta. Delta is a subgroup of gamma and still remains such, but different copy of delta is mapped or is used in this context. It's a direct sum of additive groups. We consider subgroups theta, that is, we have gamma plus delta, so we must have 2 components, gamma 0, gamma and gamma, that's a subgroup. Of course, isomorphic to gamma. Sigma is our whole group. And lambda, that consists of 0, 0, and 2, 0. That's a subgroup of theta. M is the nearing of all mappings of sigma into itself, leaving the 0 element fixed. And N4 is a subnearing of M, consisting of all mappings from M, which map lambda, theta minus lambda, and hence also theta into itself. N4 contains the identity of M. Sigma as an N4 module is monogenic. The generators are the elements gamma 2. If there is a 0, then an element of sigma with 2 in the second component would be not could be not reached. Sigma is also an irreducible N4 module. Does it move? To show this, we consider the subgroups sigma, theta, lambda, and 0 subgroup. Let N be in N4, which maps 0, 2 on 0, 0, and 2, 2 on 2, 2, leaves 2, 2 fixed. Then we have 2, 0 plus 0, 2 times n minus 0n is to 2. And this is not in theta. Hence, theta and lambda cannot be N4 submodules. This contradicts the defining property of submodules. Hence, sigma is an N4 module of type 0, being irreducible. Nj, N4, is contained in the annihilator of N4, annihilator in N4 of sigma. This is 0. Hence, we have an example of J0 and 4 equals 0. Lambda and theta minus lambda are N4 modules of type 2. Their generators are 2 and this residue class, respectively. The N4 annihilators of A of these and of this one and so on are modular right ideals of N4. Their intersection K must contain dN4. K annihilates all elements of the form gamma 2 and 2, 0. The elements 1, 0 and 3, 0 of sigma are mapped by elements of K onto 3, 0 and 0, 0 respectively. Hence, for all K1, K2, and K, we have K1, K2 is 0. Hence, K is nilpotent, and by a previous result, we have K is in D and 4. Conclusion, K must be equal to D and 4 because it also contains this. And we have J0 and 4 unequal to D and 4, which is in quite proper and nice notation J1/2 of N4. Okay, that's what I prepared. We could, let me say, this is this gives ample opportunity to look what can happen. The famous geometer Marshall Hall was asked what is the definition of a projective plane, and he said, smiling, every damn thing can happen. I wouldn't say this is a proper definition of a Near-ring, but I think with these very small Near-rings, you can see quite a few situations which seem to be rather artificial, but they really happen, dealing with group mappings of relatively simple, even abelian groups. All right. We will have when okay, we will meet again in a week. Are there remarks or questions which I could maybe answer right now or in the next session? Well, not so. You have you have the possibility to write me an email, and I'll be happy to answer as quickly as I can, if I know the answer. That's, of course. Well, that was it.
Okay, so thank you, Gerhard, very much. Maybe it seems to me that there's a misprint in a line close to the end that is on the page which you call example 9.
Yeah, the examples are example 9. Yeah, here. Where is a misprint?
When you show that sigma is of type 0, a little further down, still further down, still further down. Yes, here. The last line you see, you wrote then, and then parentheses 2, 0 plus 0.2 times n, and then minus, and I think what you want is minus 0.2 times n.
Oh, yes, I'm sorry. Yeah, yes, of course, of course. There is 0 times 2, 0.2 times n.
Yeah.
That's this is missing. I'm sorry. I'm sorry. And thank you
no
very
problem.
much. That should be corrected. Thank you very much. Yeah. Otherwise, it doesn't make sense. Oh, no. Okay.
Things like that happen all the time.
Yeah, this I decided to have a different numbering for the examples because I was in the beginning or in preparation. I wasn't sure when I should this insert. Yeah.
No
Okay.
problem. We found it.
More mistakes? Hopefully not.
Not that I know of.
Okay. Well,
Yeah, then thank you very much.
See you again in a week.
See you again, and we'll work something out for you, Bernardo, concerning an effect. Okay.
Okay, thank you.
Okay.
Okay. See you.
So see you. Bye-bye.
Bye-bye.
Thank you.
Thank you.